So the other day, we left off talking about circular motion, uniform circular motion. Okay, so just quick review here of the things we covered. Uniform circular motion means the object is moving in a circle at a constant speed, but not a constant velocity, because in order to go in a circle, your direction is always changing. And in order to turn something, you have to be exerting a force that's causing it to turn. That turn is directed, or that turning force is directed where? Towards the center, which we call centripetal. So the object is not only accelerating towards the center with centripetal acceleration, it is also being pulled towards the center by a centripetal force. Okay? If that centripetal force disappears, then so does the centripetal acceleration, and the object then travels at a constant velocity, meaning it will no longer curve, it will travel in a straight line. Okay, and that was the whole David and Goliath thing. We watched the video, okay, illustrating that, yeah, once that force is gone, the rock travels in a straight line, and it can do so at high speed. Okay, so we have to remember that centripetal means center seeking. Okay, that centrifugal stuff that we talked about, that's just inertia. That's the natural desire of something wanting to go in a straight line. All right. You probably all got that friend who, when you're in the car with them, they take corners at a high rate of speed and force you to grab onto the holy crap bar. Okay, you know that thing on the C-pillar that you can grab onto. Okay, because as they go around a corner, you're always the guy who leaves a face print on the window. Okay, because that's which direction you want to go, unless of course they're turning left, in which case you like wind up trying to get across the front seat somehow. Okay, but in this turn, the passenger would be thrown, and I'm going to use that in quotations because you're not really thrown. There's not a force making you go that way. It's just your inertia, okay, wanting you to do that. All right, what keeps you in the car, hopefully, is the seat belt you're wearing and the door. Okay, but if you're in like a Jeep with no doors, you definitely want to wear the seatbelt, because if you don't, you'll end up traveling in a straight line, and that won't be good. Okay, and I've seen that happen. Oh yeah, when I was in high school, there's a guy with a Jeep. He never had the doors on, and he would, take corners really fast. And one of his buddies wasn't wearing the seatbelt and wasn't expecting it, and out the door he went. Okay? Luckily, he wasn't going that fast, and he just kind of rolled through the intersection, and there was nobody coming. Yeah. Well, oddly enough, it did actually look a little like that, but that between that and like a log rolling, but yeah, somewhere in between. Yeah, the lesson to be learned here is keep the doors on and wear your seatbelt. Most importantly, wear your seatbelt. Yeah, don't be stupid. Okay, so if you take this corner here that only has a radius of 320 meters at 28 meters per second, how are you going to feel compared to this corner at the same speed? Well, I won't have more force, but I'll certainly feel more thrown to the outside because this corner is tighter, right? This will require more centripetal force to keep me in the corner. Now, when I'm going around a corner like this, if it's like a level corner, we call that an unbanked corner, what force keeps me in there? What force keeps me from sliding out of the corner? Friction. Yeah, an unbanked curve, which is what most corners are, rely entirely on friction to keep you from sliding out, which is why when it gets icy, it's very easy to turn a corner and just keep going straight. You've all had that experience, right? Okay, first time it gets snowy or icy and you're going around, you turn and nothing happens and you just keep going straight. So your instinct is, I'm going to slam on the brakes and turn the wheel even more. Except that doesn't help. If you doubt me, watch Canada's Worst Driver. They do this test every single season, the slippery corner, okay? And they have to slow down gradually and turn slightly, and then they don't run into the styrofoam blocks that make up the walls, okay? But inevitably, what people do is they hit the brakes lock up. Even if they're anti-locks, they still lock for a little bit, and the car just slides in a straight line, inevitably right into the wall. All right, we don't want that. We need friction there to act as a centripetal force. Okay, in the absence of friction, you slide in a straight line. Okay, all right. So what we want to do is compare the centripetal acceleration of the small corner versus the large corner. So the centripetal acceleration of this corner should be very what compared to that one? high. Yeah, it should be much larger on the small corner. All right. And the reason for that is we learned last week, okay, that centripetal acceleration is v squared over r. The speed for both of these corners is 28. It's the same. Okay, but r is much bigger in the second corner. In fact, it's 3 times bigger. So the acceleration in this corner should be how much of the first corner? 1/3. I got 3 times the radius. I'll be dividing by a number 3 times as large. I should have 1/3. Okay, that means I only require 1/3 the force of friction on this corner than I do on this corner. That's why you want to take corners as wide as possible. The sharper you turn a corner, the more likely you are to slide out of it. Okay, so we'll do those calculations here real quick. Okay, so the centripetal acceleration of the first corner will be 28 squared divided by 320 meters. All right, so my centripetal acceleration on that corner is 2.45 meters per second squared. Now, I could write into the center, but do I need to? No, I was solving for centripetal acceleration. It's by default towards the center. All right, now the centripetal acceleration in the second corner, 28 squared, but now divided by 960 meters, a much bigger corner. Okay, pretty sure that'll be 1/3. Yep, of that number. Okay, so 0.1867. So a much more pleasant experience for the occupants of the car than in the first one. Okay, everybody all right with that? Okay, so you take a corner wider, you're going to have less centripetal acceleration, and as a result, require less centripetal force to keep you successfully turning. All right. And that's often why, if you've ever watched like racing on television, okay, a race car driver doesn't take the corner like this. Okay, they get wide, right toward the outside, cut as close to the apex of the corner, and then do this. Because in actuality, what they're doing is increasing the radius of the corner by doing that. That means they can go around the corner faster without losing control. Okay, that's why they cut the corners that way. All right. Any other questions on centripetal acceleration? Okay. Very rarely are you ever asked to use this formula. We just need to understand the relationship between radius and centripetal acceleration, okay, and speed and centripetal acceleration. That's what we'll look at next. If I increase my speed, what's going to happen to my acceleration? Increase in what way? Exponentially, because v is squared. All right. So that's what we just did there, right? And I won't do an example of speed. We'll talk about that when we get to centripetal force. Okay. So I want you guys to answer for me number 2. And number 5 and number 6. Okay, so 2, 5, and 6. Okay, I want you to have a look at those, think about them for a little bit here, and then we'll talk about them. Okay. At question number 2 here, okay, we just talked about a car making a turn without skidding. The centripetal force is being provided by friction. Okay, ball is tied to the end of a rope. Yeah, the tension in the rope. Okay, moon moving in circular orbit around the Earth. Gravity. Okay, so there's our centripetal forces there. All right, if I'm pedaling a bike at a constant rate, but it has oval tires, it's not going to be pleasant. Okay, it's going to be a very unpleasant ride because it's going to be very bumpy because your speed is dependent on the radius of the circle and the period. Well, for an oval, this number is not constant. It's always changing. So your speed will go up and down, up and down, up and down as you're going essentially uphill on the oval and downhill on the oval. Okay, that's what happens if you bend one of the wheels on your bike. It essentially becomes an oval wheel, okay, and it doesn't ride nearly as well. Okay, and it's hard to keep the tire inflated on an oval tire because you have to have an oval tire on an oval wheel. Okay, now for number 6, with the bike tire. All right, so here's my tire, okay, and I've got a rock stuck in it right here. What's holding the rock in the tire? Okay, what force is between the treads and the rock? Friction. Okay, friction is holding it there. Now, that force of friction can only, it can be sort of, there's a maximum amount for it. Okay, there's a maximum amount of friction that can be provided by the squeezing of the grip, okay, or the tread against the rock. So the only way to dislodge it is to make sure that the rock is going fast enough that the force required to keep it moving in the circle, that is, keep it in the tread, isn't big enough. Okay, and so as a result, it'll fly out. And when it does fly out, it'll fly out like this, in a straight line, which then becomes a projectile arc, which usually encounters my windshield. Okay. Yeah, and then they come out, yeah. Okay, so when are you most likely to get a rock chip in your windshield? Well, not just, it could be anywhere. The highway, yes, is where you're most likely, but when the car in front of you is doing what? Accelerating, speeding up specifically. Okay, slowing down, it shouldn't happen. Okay, but speeding up is when they're most likely to throw a rock that is stuck in the tire. Because usually they have bigger tire treads, so more stuff can get stuck in them. Okay, if you're looking at like a performance car, they're less likely to get, their treads are softer, so they're going to throw them at slower speeds. And their treads aren't of the same pattern. Like a big truck is going to have deep tread patterns, and so rocks can get stuck in there really deep, and then they don't come out until the truck is moving really fast and can really throw that rock. Okay? Yeah, so following distance is important, especially if the car, if someone has just pulled onto the highway and they're accelerating up to speed, get in the other lane or drop back, because that's when they're most likely to throw the rock. Okay? It's in that situation, right? Now, most of the time, what people say is, well, I take a stick. I'll put the stick in the tire. Okay, sure. If that's your front tire, you're going to stick the stick in the tire, and what's going to happen to you? It's going to get stuck between the forks, and over you're going to go. Okay? No, you don't put a stick. You're moving. You're going to dislodge a rock while the tire is rotating with a stick. I would like to see that, because I like watching people fail. Okay, that would be a fail army one, that would for sure. Okay, so no, we wouldn't want to do that. Just go faster, and it'll eventually fly out. Okay, and that's why as a kid, when your mom would get mad at you, you ride home when it's raining and you got dirt all up your back, right, from your bike, because the faster you go, it spits more, okay, of that mud up onto your back. All right, so that's it for kind of uniform circular motion. We'll talk a little bit about centripetal force stuff here. Just right now, kind of in general, and then I'll go into the rest of it tomorrow. So centripetal force, okay, is going to be a net force. It's going to represent net force, the same as net force was in the last unit. Now, in the last unit, we calculated net force by going mass times acceleration and the vector sum of all forces. That's still going to be true here, except the only directions we're going to have are into the circle and out of the circle, and there aren't too many forces that act like directly out of a circle. Okay, normal force is really about it, and we won't get into that till we get to vertical circular motion, which isn't uniform. Okay, so for right now, if I want to calculate the centripetal force, understanding that it's the net force, I'm going to take mass and multiply by centripetal acceleration. Now, the formula for centripetal acceleration, we just said, is v squared over r. So this is our formula then for centripetal force. That will be the most fundamental formula we have in this unit. It will be like Newton's second law in the last unit, because it's still Newton's second law. It's just applied to a circle. Right? So the challenge in this unit is identifying the forces that are acting. Okay? If I've got a car going around a corner, then the force acting as the centripetal force is friction. If I've got something whirling around on a string, it's the tension in the string. Okay? Then I would set that equal to the tension or the force of friction. If it's something going around a corner, then mv squared over r is going to be equal to mu times the normal force. Everybody with me there? Okay? So it's really not changing a whole lot from last unit. It's just now it's applied to a circle. Again, V is squared in this formula. So any increase in V means what kind of an increase in FC? Exponential. Now, here's what that means for you going around a corner. If you double your speed around a corner, you're going to require how much more friction? 4 times as much friction. So it doesn't take long before even a small change or increase in the speed going around a corner for you to lose it, for you to skid out, okay? Because you can't expect the force of friction to exponentially increase for you, okay? Or to be able to just be that big, okay, for whatever speed you're going to go at. So eventually you will just spin out, right? And that's what car manufacturers do when they're testing the cornering ability of a car. They just have a circle painted on the ground, and they just tell their test driver to drive around that circle at ever increasing speeds until they spin out. Okay? And then that allows them to calculate essentially the cornering ability of that car measured in as a unit of acceleration or G-force. Okay? Most vehicles can usually corner around a skid pad like this at about 0.8 G. All right, a really high-end sports car could be over 1 G, which would mean you would feel a force. If you were pinned against the door, it would feel like you were laying on the ground. There would be that much force pushing against your shoulder. Okay, 1 G. Right. If you're looking at like, F1 drivers and stuff like that, they have to wear like the full 4-point harness and the head and neck restraints because the forces acting on them are incredible, okay, when they go around corners. Okay, is that making some sense? Well, I mean, they would do a little more analysis than what we've just done. We would be assuming all vehicles would be the same. But yes, center of gravity makes a big difference because that creates a rotational force in addition to the circular part, right? So what Logan's asking is, if I'm looking at this from ground level, a lower vehicle, center of mass will be lower to the ground, and it'll have less inertia wanting to do this, right? A taller vehicle has more mass higher up, so it wants to do that more easily. And you see that lots of times with like U-Hauls, right? People don't think about where to put the weight when they pack them, okay? Incidentally, so this is good for you for later in life. Put the heaviest stuff on the bottom. A, you don't have to lift it. And B, it's safer. The heavy stuff closer to the bottom means your center of mass is closer to the bottom. You start putting a bunch of weight near the top, and this thing is more likely to want to tip over. Okay, because there's more inertia up top. There's more mass up top. Okay, that's why like all SUVs have those big stickers on. If you drive an SUV, like flip down your sun visor. On the back of there's always this rollover thing. Okay, because SUVs tend to have a lot of weight higher up. Okay, and so they're more likely to roll if they're taking a corner at high speed than something lower to the ground. Okay, making sense? So think about that when you pack stuff. Okay, people who pack semi-trailers and things like that, that's stuff that they have to think about. They always pack the heavy stuff lower, okay, and the lighter stuff up top. Because A, it's easier to lift the light stuff, but also B, from a safety standpoint, you do not want a ton of weight near the top of the trailer. Okay. All right, so that's centripetal force. Like I said, the big challenge is going to be identifying what's acting as a centripetal force. It could even be gravity. If we're talking about the moon orbiting the Earth, okay, that's a lot of gravitational force, right? We're talking about 2 big masses, and we're talking about big distances and things like that. Okay. All right, I think we will leave it there so we don't get too far ahead of my period 2 class who had to do registration this morning. Jackson, question? No? Reminder, guys, that lab we did on Monday, that's due on May 1st. Okay, so that's after Easter. All right, make sure you get it done so that you can, ask questions if you need to on the Monday or Tuesday when we come back.